Swayam Prabha. Digital India. Educated India.
Welcome. So in the last class we have started looking at dual fitting, and using dual fitting we have analyzed the greedy set cover algorithm. So in today's class we will use a greedy algorithm for solving a generalization version of set cover problem, and we will analyze it using dual fitting. So dual fitting. So our problem is set multi-cover. So what is the input? Input is again a universe U and a collection of sets with costs and cost function C from this collection to real number, and for each element in the universe a certain requirement, how many times it must be covered. So R E in U. What is the output? Collection of S J1 to S1 prime to Sk prime in cal S such that for each element E in U, E is present in at least RE sets in S1 prime to Sk prime, that is 1, and sum of costs is minimized. Okay. So we'll extend the greedy algorithm for set cover naturally to this to this more general set cover. So greedy algorithm for set multi-cover. So let us say we say an element E is alive if it appears less than RE many sets picked so far. Okay, and in every iteration the algorithm picks the most cost effective set, that is the set with minimum average cost per alive element. Okay, that means if for a set S, if it contains 10 alive elements, then its cost effectiveness is cost of that set by 10. That is the average price with which it covers an element. The algorithm halts when no element is alive. Again, the cost is distributed across the elements covered. So, when S is picked, its cost is distributed equally among the alive elements that it covers. That is, if S covers an element E for the jth time, then price of EJ, price of E comma J is the cost of the set picked by number of alive elements in S. Hence, alg, the cost of the solution picked by the algorithm is sum of CS S picked by the algorithm and because the cost is distributed among across its alive elements, this is sum over E in U j equal to 1 to R E price of E comma j. And also because the algorithm picks each set at most once and picks the most cost effective set in every iteration. So, since the algorithm picks each set at most once and picks the most cost effective set in every iteration, we have price of E comma 1 is less than equal to price of E comma 2 less than equal to dot price of E comma RE. So, price of an element is a non-decreasing as more of its requirements are fulfilled. Okay. Now, we will analyze this algorithm using dual fitting. What is the first step? The first step is to come up with a dual assignment which may be infeasible, but which gives a bound on alg. So, for that, so what is the dual linear program? So, let us recall the or let us write the linear programs. Now, minimize summation S in cal S C of S x of S and then subject to look at all the elements for every element E in all sets which contains E. Among all those sets, RE number of them should be picked. This is for all E in U, and XS is in between 0 and 1. So, this is the ILP formulation. Now, we relax it. Minimize C of S XS S in cal S subject to this constraint is there that S in cal S E in S X is greater than equal to RE for all E in U, and XS is in between zero and 1 for all S in cal S. Now, here because each element needs to be covered more than once, we cannot simply drop the constraint that xs is less than equal to 1. The minimum solution means if we simply drop xs is less than equal to 1, the best solution may pick more than one copy of xs of an element s, of a set s. So that's why we need both the constraints. And now to write it in the normal form, what we need to write is in the standard form that xs is greater than equal to minus xs is greater than equal to minus 1, because in the normal form I need to write the constraints, in the standard form I need to write the constraint is greater than equal to form and xs is greater than equal to 0. So this is the LP, the primal LP. Now let us write its dual, maximize. Now we have more constraints, so I need to multiply these constraints for every E in U with a variable called YE, and suppose for each S I have a constraint minus xs is greater than equal to 1, this is multiplied with zs. So the right hand side becomes summation YE times RE minus summation zs, which I maximize. So maximize summation YRE times YE, E in U minus summation S in calis ZS, subject to I have the coefficient for every xs, and the coefficient for xs is summation YE, E in ES minus ZS, subject to summation E in S YE minus ZS. This is less than equal to C of S for all S in calis. Of course, we have YE greater than equal to 0 and ZS greater than equal to 0. This is for all E in U, this is for all S in cal S. Okay, so this is the dual. So the first step of dual fitting is to find a dual assignment which sort of matches alg or which gives a lower bound on alg, which gives a upper bound on alg. So alg is less than equal to something, but often it will be equality. So what should we set? We set YE to be equal to alpha E, which is just price of E comma RE, and ZS also we set, this is for all E in U, and ZS equal to beta S, which is summation E covered by S. Covered by S in the algorithm. That means what? That means in the algorithm, algorithm picks this set S to cover certain copy of the algorithm. So when S is picked, that means then E was alive. Summation price of E comma RE minus price of E comma JE, where S covers E for the JEth time. If S is not picked by the algorithm, this is if S is picked. Otherwise, if S is not picked by the algorithm, then we set Zs equal to beta s equal to 0. So, first we need to show that the dual objective with this setting of dual variables, how does it connect to alg. So, summation Re alpha E E in U minus the Zs, if S is not picked, is 0. So, this sum is over the set which is picked by the algorithm, minus beta S in S, this is E in U Re times price of E comma Re, this minus S picked by algorithm. This is price of E comma Re minus price of E comma J. Yeah, let me just write jth copy. Now, because this is a valid solution, there are Re many sets which picks E, and hence this term price of E comma Re gets cancelled with this, and this is what we have is sum of E in U sum of j equal to 1 to Re price of E comma j. This is nothing but alg. So, the first part is to show that alg is at most the dual objective function, but this is not a valid dual solution. So, we define ye hat to be alpha E by Hn and Zs hat is beta S by Hn. Next, we claim that ye hat E in U Zs hat S in Calais is a dual feasible solution. Proof. Okay. So, what are the dual constraints? For each set I have a constraint. So, let S in Calais be any set containing k elements number the elements in the order they stopped being alive. So, let S equal to E1 to Ek. That means element E1 is the first one to have stopped being alive, followed by E2 and so on. Now, two cases. First, case 1, algorithm does not pick S. Does not pick S. Then we have what? Then ZS is 0. First of all, let us see what are the elements there. A price of EI and REI. You know, when EI, the REI copy of the last copy of EI is picked, this set is still available to cover it at the cost of CS by K minus I plus 1, because EI plus 1 to EK, those elements are alive. So, at this price, this set is available to cover them. So, and we pick the most cost effective set. So, price of EI is less than equal to this. Okay. Now, let us see. So, what are the constraints? The summation YE RE. So, summation. So, what is summation YE hat E in S minus ZS. I need to show this is less than equal to CS minus ZS. Now, summation, this is 1 I equal to 1 to K, because it has K elements. Price, what is YE hat? Alpha E by HN. And what is alpha E? Alpha is price of E comma RE. This is price of EI comma REI 1 over HN and minus 0, but price is this. So, this is less than equal to 1 over HN summation CS K minus I plus 1, I equal to 1 to K. So, this is CS HK by HN, which is less than equal to CS. So, the constraints are satisfied when S is not picked. Similarly, you can check it that it can be verified that in the other case when S is picked, the dual constraint is also satisfied. Okay, so this shows that this is a dual feasible solution. So, what? So, opt is greater than equal to the dual objective function at this value. So, what is this? This is this summation RE YE hat E in U minus summation ZS S in this ZS hat. And what is this? This is H of n summation E in U RE YE minus summation S in cal S ZS, but this is alg, this is HN, this is 1 by HN This is alg by Hn. So we have alg by Hn, this is less than equal to opt. Sorry, alg by opt is less than equal to Hn. So hence we have a Hn factor approximation algorithm. Okay, so let's stop here for today.